So in bonds, and we're talking specifically here about covalent bonds. Remember, with ionic bonds, we just studied the 5-step process of ionic bonds. What's that process called when we looked at the process of an ionic bond formation? What's that called? The what cycle? The Born-Haber cycle. The Born-Haber cycle is the 5-step process that neutral metal and neutral nonmetal go through to then ionize and form a new solid compound. Okay? But this is covalent. So we're looking at covalent bond energies and what happens in covalent bonds. So in order to break a bond, right? Remind me what happens in a covalent bond between the electrons. What do? They share. They share. A covalent bond is sharing of electrons. So that means in order to break bonds, we have to add energy to the system. And then it would be considered endothermic, right? We're not going to deal a whole lot with this endothermic, exothermic. I know that's your guys' favorite topic, but we don't deal a lot with that, okay? If I'm going to form bonds, they actually release energy. So that's kind of general overview, and it gives us an idea as to our bond energies on our table here, but we're looking at how much energy is required to break bonds here because all of our H values here are positive, okay? All right. When we look at bond energies, we're going to calculate delta H of a certain reaction. And this is a lot more intense than, it's less intense than what it looks, okay? This equation makes it seem more difficult than it is, but it's really simple. Okay, let's walk through what this means. Delta H is change in enthalpy, right? And what is that? Do you know what that Greek letter means? You know what it stands for? Anything? Do you know anything about that Greek letter? Really? Okay. No, it's not an E. That's a sigma. Mr. Morris, am I right? That's called sigma. Yeah. Okay. So sigma means the sum of. All it means is the sum of. So you're going to add up all those things. Okay. The sum of. Do you know what do we use for N? What variable does N usually carry? PV equals N. Moles. Yes, moles. N is moles. So the sum of the moles of a certain type of bond that is broken minus the sum of all the moles of the bonds that are formed. Okay, so the equation there makes it look a lot more intense, and I wouldn't even necessarily say that you need to know this equation specifically because we're going to know what it means, right? We're going to know how to do the math that goes with it. So delta H is the sum of energy required. E is the sum of all the terms, so all the reactants added together, all the products added together. Okay, reactants minus products. N represents the number of moles of a particular bond. D represents the bond energy per mole of the bonds. Okay, and it always has a positive sign. So we're going to take bonds broken, that would be the reactants, minus the bonds formed, which would be the products. Would we agree with that? Right? Reactants are breaking down, products are building up. So we're going to take the reactants and all of their bonds that have been broken, the energy that's been released in broken bonds, and we're going to reform that into products. Okay. Let's look at our first problem. All right. There's no better way than to just jump in and solve it. Okay. So this is why I taught Lewis structures earlier in this chapter, because I have to know what type of bonds are found in this molecule. Sometimes it gives us a hint, like that guy. Sometimes it doesn't. Okay, so I have to know what types and how many of those types of bonds are present in that molecule. So I'm going to go ahead and just draw the Lewis structure based on this hint, okay? CH3NC, okay? You see this? This is our molecule right here. It probably is going to look something like this. Carbon, triple bond to nitrogen, carbon, H, H, H. Right? Would you agree it's going to look something like that? Okay, I'll allow it. Thank you. Okay, if we want to check valence electrons, we can. 4 plus 3 plus 5 plus 4 gives me 16 electrons. So 2, 4, 6, 8, 10, 12, 14. Where would my last one go? Where's my last lone pair going to go? I think it's got to go carbon. Carbon's the only one there with an incomplete octet. Even though that's pretty gross because carbon does not love that, okay? Carbon does not love it. Is there a formal charge on either of these? Rethink that. Yeah, is there a formal charge on either of these? Yeah, which one would have a +1? No. Carbon, how many, let's think about it again. How many electrons does carbon contribute? 4. And how many does it have directly around it? So what's its charge? And how many does nitrogen contribute? 5. And how many does it have around it? 4. So it ends up neutral, right? If nitrogen has a +1, carbon has a -1. It's just not ideal, right? It's just neither of them are happy about it, okay? But it's there. So that's what my Lewis structure looks like. Now, every time we do a problem like this, do we need to bother with the formal charges? No. I just, like to make sure everyone's on their toes, okay? But when we set up our Lewis structure, we're going to figure out how many bonds in each type we have. So over here, I have, on the reactant side, I have how many, do I have any carbon to hydrogen bonds? I have 3 of them. So I'm going to take 413 times 3. Okay. And actually, the way I like to write this out, I don't really have room to do it right here, but I like to write out here, carbon to hydrogen equals 413, and there's 3 of them. Okay, then I also have a carbon to nitrogen single bond, and that is 305. How many of those types of bonds are there? Just 1. And then a carbon to nitrogen triple bond, which is 891. And so I'm going to add up that whole side, that whole reactants side. I don't care about the lone pair, right? Because we're not breaking that bond. Yeah. Not to say I don't care about it. I mean, obviously I care. Yeah, I mean, for real. Okay, 413 times 3 plus 305, 891. So that gives me on the reactant side 2435 kilojoules per mole. Did I have any coefficient there? No. If I did, I would have to take that into account, right? If I had 2 of these molecules, I would take that whole thing times 2 because I'd be breaking twice the number of bonds. Capiche? Okay. All right, so I don't have a 2 there, so I'm not going to do that.
One carbon nitrogen bond is 305, but 3 is not just 3.
The next one looks really similar, doesn't it? So why is it not exactly the same? Why doesn't it have exactly the same bond energy? Yeah. Right, and we're going to have a different. We're not going to have a carbon to nitrogen bond. We're going to have a carbon to carbon bond. Because our compound will look something like this. C to N, C, H, H, H. And so there our lone pair goes there. So which of those structures is more favorable? The reactant side or the product side? Product side. Because now none of ours have a formal charge. Right? Everyone's happy. So that's why it happened. Right? Okay. So now I've got carbon to hydrogen. I've got 413 times 3. I've got a carbon to carbon single, which is 347. Is it freaking you out here that I'm putting these equal signs? Do they make you think they're double bonds?
I have before a triple bond was it. Equal sign for the other line.
All right. Carbon to nitrogen. Maybe I should do this. If I do that, what do you think? And then it looks like a lone pair. I'm out of options. Oh my gosh. I can't even think about a single line that looks like a... Like that? I don't have time for that, Evan. An arrow. Thank you. All right, an arrow. Yes. Oh gosh. You're right. You're right. We have no options. It's not equivalent to. Like that? There's nothing. All right.
I think we just stick with the equal sign.
I think we'll just do equal sign. All right, carbon to nitrogen's 891. So let's add it up.
If you think about it, it's not bonded to the number.
That's true. It's not bonded to the number. Okay, so plus 347 plus 891. So on my reactant side, I get 2477. And so that means my delta H for the total reaction will be, well, actually I do want an equal sign there, at 2435, reactant side minus product side. Okay, and that means my delta H for the reaction is negative 42 kilojoules. Okay. So my final answer can come out negative, but each of my sides will never be negative, right? My independent sides would never be negative because my bond energies are all positive values. So my final answer could come out negative, but my independent sides wouldn't be. Seems easy enough, right? Yeah.
Would it be?
No. I'm wrong. My final answer is just kilojoules because I already took into account the per mole here by using the mole ratio there. Yeah. So just kilojoules. Yeah. Okay. The tricky part with this, honestly, is making sure your Lewis structure is right. Right? Making sure that you drew it accidentally as a single bond, but it should be a double or triple. So you got to make sure that your Lewis structure is right before you can move into actually doing the bond energies. Because using the table and doing the math is not hard, right? We got to make sure that our Lewis structures are right. Okay, not all the time will it give us a hint like this, right? Giving us the triple bond there was helpful. Okay, let's look at the next one. I put the bond energies up there in the right-hand side. But now our reaction gets a bit more complex. Yeah. Okay. Are we good?
Just like it.
Okay, let's try the reactants sides. CH4, do I need to draw out that Lewis structure? All right, I'm going to have a CH bond that equals 413, and I know I've got at least 4 of them. Yeah, you're gonna get familiar with 413. Okay, next one, Cl2. What's that molecule look like? Single bond, double bond, what do we think? Yeah, I would say we're just going to be here, right? They each contribute 7, so it's just going to come out pretty clean to Cl. Okay, so that means we're going to have a Cl bond. But how many of those do we have? 2. And why do we have 2 of them? Is it because of this? It's because of the mole. It's not, right? In this molecule, I only have 1 of them. But this says I call for 2 of those molecules. So that's really important. When we see Cl2, it doesn't automatically, that means we have 2 bonds, right? This alone would only have 1 of those types of bonds. Okay, so that means I'm at 239 times 2. And then for fluorine, same thing, right? Fluorine to fluorine bond, is it single? 154, and I'm going to have 2 of them because I have 2 moles of that, okay? And so that's my whole reactant side. 413 times 4, oops. I don't know, about 2438, okay? Took into account my mole ratio on both of those. I didn't have a different coefficient on the first one, so I'm not worried about that. So we're all good on the reactant side. On the product side, can you envision what that molecule looks like? CF2Cl2? What do you think?
It's just like 4Cl.
Yeah, it'd just be tetrahedral, right? So we would have carbon to fluoride. And how many of those bonds would we have? We would have 2 of them. Carbon to chloride bonds, how many would we have? How many bonds? Uh-huh. Do you see what that looks like? F, Cl, right? I don't think we'll need double bonds there. So all good. What about the next one? 2HF. Between H and F, what type of bond are we predicting here? Can hydrogen have a double bond? No. So H to F single. How many of those bonds do I have? 2. 2 in total, right? 1 per molecule. So that would be 2 total. And then HCl would be the same, right? HCl would be a single bond between H and Cl. And so that means I'm going to take 427 times 2. On the product side, tell me what we get there. Okay, yeah, that's what I got too. 2438 minus answer gives me negative 1194 kilojoules. Okay, what do we think about that? That seems simple enough, right? I think the next part of your notes talks about Lewis structures, but we went through that at the beginning. Okay, or did I not even print those for you?
There's something there.
There's something there. Okay. The next part of it reviews Lewis structures, but we really already went through that. So that really is the end of our new material for the chapter, right? Lewis structures, formal charge, Born-Haber cycle, covalent bond energies. All right, so if I look at the first one, can we assume it's not going to be a single bond there? All right, probably not. So do you know right off the top of your head what bond it is going to be? Or do you need to draw it? Okay. I don't hear a consensus yet. I don't know. That's what I'm asking. So if it goes like this, if I have a double bond, how many electrons am I allowed to have? 10. 2, 4, 6, 8, 10, 12. That's no good. So that's not going to work. Just quadruple bond, yeah.
Is it gonna just have to like?
So let's. How many am I supposed to get again? 10. 2, 4, 6, 8, 10. So that's no good. So I got to move this guy into a bond. And then I'm going to have to do it again. So yeah, I'm going to have a triple bond. Okay. Well, okay. That's an option. So carbon to oxygen triple bond. Is it on there? Oh, 1072. Okay, and then H2 has to be what types of bonds? Single bonds. So H to H is 432. And how many of those bonds do we have? 2. Okay. So 432 times 2. $1936. Right, and we're always going to go reactants minus products here. All right, the other side. Can you get a Lewis structure put together for that, or do we know bond types already? Remember, this gives us a hint at our structure. All bonded to carbon, but also bonded to carbon. Right? Oxygen is also bonded to carbon here. So there's our 3 H's. Here's our O, H. Right? The H that tags along at the end has to be bonded to oxygen. So we've got 4 plus 3 plus 6 plus 1. So 14 electrons, I think, in our structure. 2, 4, 6, 8, 10. Yep, bingo. So actually we ended up with all single bonds here. So let's look at bond types. We've got carbon to hydrogen. We know it's 413. Good. And we've got 3 of them. We've got a carbon to oxygen single. And that's 358. And then we've also got an oxygen to hydrogen single. Yes, thank you. 467. And so that gives me about 2064. And so when I take reactants minus products, I'm going to get negative 128 kilojoules.
Are they usually negative?
What did you get?
2,000. Help me draw this one time.
Two carbon.
Oh, I see. It's here.
E.